Okay, I guess we can start. So welcome everyone. And today we are happy to have a talk by Nikolay Bobev. And he will speak about large and efficient functions, holography, and black holes. So please start.
Thank you. Thank you so much for inviting me. I should say a few personal comments. I was educated in Bulgaria, in Sofia, as a student. And there, I think almost all of my teachers there were educated in Moscow, or most of them at least. So it's a special pleasure to be giving this talk, although virtually. Hopefully one day I'll be able to come to Moscow in person. Good. So I'm going to be speaking about ADS-CFT, basically. Some work that we did about large and partition functions and how all of this connects to holography. And this work appeared in the papers that are listed here. And it was done mostly with these two people, Junho, who is a postdoc here in Leuven, and Val, who was a postdoc in Leuven and is currently in Paris, Saclay. Good. So I should also say that I'm not sure what the background of the audience is, so you should feel free to interrupt me at any point and ask any kind of questions, or if it's too elementary, you should ask me to speed up. If it's too hard, you should ask me to explain more. Just feel free to interrupt me. Good. The motivation for this work comes from the ADS-CFT correspondence, where essentially one way to formulate the correspondence is as an identity between the partition function or the path integral of a CFT in the presence of some background sources, J, and then the path integral of string or M theory, again with some specific boundary conditions on an asymptotically anti-de Sitter space. And usually, or in many instances of ADS-CFT, people try to compute the right-hand side here, or at least in some approximation, like a supergravity approximation, and learn about the left-hand side. But we now also have some tools to compute the left-hand side, specifically using what's called supersymmetric localization. And so in some instances, you can hope to use the left-hand side to learn about string and M theory. And in this talk, I'm gonna speak about a specific instance of this case where we can study this large N expansion of some quantum field theory and learn about subleading terms in the supergravity approximation to a string or M theory. And why is this interesting? You may say, well, on one hand, it's really hard to quantize in general string theory on anti-de Sitter backgrounds because of the presence of fluxes. And it's even harder to say anything about M theory because, we don't have an intrinsic non-perturbative understanding of the theory. And in addition, in anti-de Sitter space or asymptotically anti-de Sitter space, you can have a black hole. And you can use, in those instances, you can use the left-hand side here to try to learn about the properties, the microscopic structure of black holes, to understand the thermodynamics of a black hole. So that's kind of the broad motivation. And of course, this sounds very, very general. So in this talk, to be specific, I will focus on three-dimensional superconformal field theories that arise from M2 branes in M theory, and their corresponding ADS4 dual backgrounds. So this will be the context that I will explore these kind of questions. And here's the plan of the talk. So motivation I've already covered. So the next thing I'm going to speak about is this ABJM theory, which is the prototypical example of such holographic CFT. And I will explain to you how to compute certain kind of observables on the round sphere for such a model. Then I will keep the theory the same, but I will change the type of observables that we study. I will explain what this index is and how to compute it. And then I will move on to the ADS part, so to say, and explain what these quantum field theory results can teach us about holography and black holes. And then I will make some comments about other examples, as well as some other observables that we were able to compute. And finally, I'll try to explain how, even though everything up to here will be supersymmetric, in the last slide, I'll try to convince you that we can also compute something that are not supersymmetric. These thermal observables in the ABJM theory specifically. Okay, so at this point already, if there's some questions or comments, you can interrupt me.
May I ask one naive thing?
Yeah, please, please.
So, like, I have very basic knowledge about this, but as far as I know, localization relies on supersymmetry, and this allows one to simplify path integral computations. But this supersymmetry is also present in the bulk, right?
Yes, absolutely.
And still, you cannot use localization to simplify everything. How is it?
Right. It's a very good question, and there's people actually have tried to use the same ideas of supersymmetric localization directly on supergravity theories, and in some cases progress has been made, especially when the backgrounds are asymptotically flat, so what's called ungauged supergravity. People like Samir Murti and Atish Dabholkar have written many papers on this. So in some instances, you can get results directly applying SUSY localization in gravitational models, but it's somewhat confusing what the rules are and what the level of the rigor is. And it's certainly confusing to me how to apply it in the anti-de Sitter context. So I will not be doing that in this talk, but it's an interesting thing to ask and study.
Thank you.
Thanks. Good. I will move now to this ABJM theory. So very quickly, what is this model? It is some specific Chern-Simons theory. It has UN times UN gauge group. It has Chern-Simons level K and minus K. It has also matter fields, so it's not a purely topological theory. And these matter fields in an n equals to 2 supersymmetric notation are organized into bifundamental chiral multiplets, A1, A2, B1, and B2. And they have a very specific interaction term in the superpotential written here. So this is like a 1-minute introduction to what the theory is. And the reason it is an interesting model is that for any k, it is supposed to describe the low energy dynamics of n M2 branes probing the space C4 mod ZK. So this ZK orbifold acts in some specific way on the C4, and when k is more than 2, you have n equals to 6 SUSY. When k is equal to 1 or 2, there's some specific enhancement of supersymmetry to n equals 8, maximum supersymmetry. And in the general case, this is SU4R is the R symmetry, which rotates these 6 supercharges, and then there's an extra U1 bosonic symmetry, global symmetry. Okay, we'll be interested in this model in the large n limit to make contact with ADS CFT, but there's actually at least 2 interesting large n limits that you can study. There may be more, but I'm going to talk about 2 of them. One thing that you can do is to fix this k to be some fixed integer, let's say 1 or 5 or 11, and then take n to be large, the rank of the gauge group to be large. In this limit, the claim is that this model is dual to 11-dimensional supergravity or M theory on this background, ADS4 times a sphere. And there's some certain identifications on the sphere, this ZK modding here. But importantly, this ZK does not have a fixed point on the sphere. So this manifold is completely smooth, S7 mod ZK. And the identification between the QFT parameters k and n and the length scale of ADS, this big L here, and the Planck scale in 11 dimensions is schematically given here up to factors of 2 and pi. So when n is large and k is fixed, we're in a limit where the length scale of ADS is much bigger than the Planck scale, And this is why we can use the supergravity approximation. That is essentially the logic. You can do something else which mimics the usual limit of a 't Hooft coupling being large or small in a large N gauge theory. And this is to define something that looks like a 't Hooft coupling, lambda, which is n over k, and then take both n and k large and keep lambda fixed. Okay? In this case, you're actually essentially exploring a different bulk dual, a different supergravity dual to the same model, which is type 2A string theory on ADS4 CP3. So as is well known, S7 can be written as a U1 bundle over CP3, and what this ZK essentially does is to reduce the size of the circle, which is fibered over the CP3. And this is why when K is large, effectively you have a reduction from this sphere to CP3 schematically. And then you have a new parameter, the coupling of the string, G string here, which is related to this lambda in this schematic way. Okay, and LS is the usual length of the string. Okay, and so in this case, we can hope to make a connection with type 2A string theory in this limit. Good. Now, this model is something that I didn't actually say, but this is a conformal field theory. So it's a superconformal field theory. And as any conformal field theory, it can be put without issues on any conformally flat manifold. So I can easily put this model on S3 as opposed to R3. So I'll be studying the theory in Euclidean signature, and I can transform just to the round sphere. And in this case, as was shown in this work, famous paper, one can use the tools of SUSY localization to reduce the path integral of the theory to a matrix integral. The matrix integral is over these numbers mu and nu. There's n of them, which essentially parameterize the scalars in the vector multiplets of the gauge theory. And there's some specific integrand, which I'm not going to explain how you obtain, but it comes out from performing the SUSY localization procedure, basically. So now we have reduced the path integral to just a matrix integral, but matrix integrals at large n are also not easy to solve in general. So one still has to do some amount of non-trivial work, and this has been approached in the literature with various ways, with various tools. I'm not going to explain what these tools are, but essentially there's a variety of methods used in this context. There's some map of this matrix model to Chern-Simons theory, ordinary Chern-Simons theory on S3 mod Z2, which has a connection with a topological string on a non-compact space. And this was used in this work to essentially solve this model in this limit. People can also do brute force numerical saddle point approximation and study the distribution of eigenvalues of this mu and nu, these eigenvalues of the adjoint matrix at large n. Or if you are smart and you have looked enough at integrable models, you can probably reorganize and see how this is related to a free Fermi gas, and this was done in this work. So anyway, the point is that we have a variety of tools to study this matrix model. And what emerges out of these calculations is the following answer. So I'm just going to give you the answer, and then we can try to understand what this answer means. Again, I'm at the fixed k large n limit. And what happens is that there is some compact way to rewrite the full 1 over n expansion. So the full perturbative series in 1 over n can be explicitly found and resums into an Airy function. So this function here, AI, is an Airy function. There's a prefactor, this curly a, which is known in some integral form, which can also be expanded at large k in this kind of a series, where these b's are the Bernoulli numbers. And then, in addition to this Airy function and the prefactor, there is a whole infinite series of what should be called probably non-perturbative effects. So these things that are suppressed as exponential in minus a square root of n. So these people also understand how to compute those in an approximate way, but there's, as far as I know, not really closed form answers for all of them. Okay, so in M theory, this essentially, the first piece will correspond to all perturbative corrections to 11D supergravity, and these exponential terms should be M2 brane instantons, which we certainly don't know how to compute systematically. But this matrix model computes all of this for you essentially with very little effort. At large n, you can take the logarithm of the path integral. So let's call this the free energy in analogy with statistical mechanics, and then expand this answer, and you will get something like this. This is very easy to obtain simply using the expansion of the area function at large n. And what you find here is this infinite series of 1 over n corrections. Yeah, and I just want to emphasize that it's easy to obtain all of these numbers. Notably, one thing that was a long time ago, I guess, a confusion, or we didn't understand why this happens, is that you begin with a theory that has the fundamental degrees of freedom are n by n matrices. This is a gauge theory of adjoint and bifundamental field. So everything is an n by n matrix. So naively, you should expect that every thermodynamic observable, like the free energy, should scale as n squared. And instead, what was known from 11D supergravity is that it scales as n to the 3/2. So there's some strongly coupled dynamics which effectively reduces the scaling of the degrees of freedom at large n. And this matrix model implements this automatically for you. It will give you this n to the 3/2 as the leading term. Okay, one thing that you can do now is, which is not very legal mathematically, but we nevertheless did it, is, so this expansion is given to you at fixed k and large n. Now, once I have this, I can close my eyes and take k to be large and try to re-expand this in this other large n limit where n over k is being fixed and lambda, which is n over k, is large. So in this way, I'm supposed, the expectation is that I should obtain an answer that looks like this. So this is given to you by the arguments of Hoft that large n gauge theories at fixed lambda should look like a string theory. So now I'm aiming to obtain some series like this, where this g, which is an integer, should be thought of as the worldsheet genus of the putative string theory. Again, I'm emphasizing that so far I have a matrix model only. So I just feel, or I have arguments that I should be able to do this, but I will actually have to do it. And indeed it works. So these are explicit answers for these FGs should be thought of as the free energy of that putative string as a function of lambda to all orders in 1 over lambda. So what I'm not computing here are exponentially suppressed terms in lambda. And okay, what we did is we have like a systematic algorithm to give you any FG that you like. So if you're interested in the genus 11 free energy of this string, I can look at my mathematical file and give you the function. One thing that happens that, you know, a priori you should not expect, but it seems to be true, is that these FG of lambda, these free energies of the string at large lambda, actually resum into very simple functions of what we call lambda hat, shifted lambda with -1 over 24. This -1 over 24 is not an accident. It came out from this k over 24. So the form of this parameter b that appeared in the Airy function determines the shift of lambda based. Okay, good. What is this good for from the perspective of ADS CFT? As I said, it's quite easy to expand this area function at large n and try to read off the coefficients. And then you can start asking, you can put your ADS-CFT hat on and start asking, how do I compute these coefficients from 11D supergravity, from ADS4, basically. And this has been understood for the first 3 coefficients, basically, with some simplifications that I'm not going to talk about, but essentially the leading term here, this pi square root of 2k over 3, arises from a non-shell action evaluation of this solution of 11-dimensional supergravity. So it is quite easy to take any solution of this form where x7 is an Einstein manifold, evaluate it on shell. This will be a divergent answer. Then there's well-known ways to regulate this answer and get a finite result. And the result looks like this. It depends only on the volume of this internal space. And if that internal space is our sphere, you get a specific volume, and you put it in here, and you get exactly this prefactor. Then the subleading term can be understood as coming from higher derivative terms in supergravity. I'm not going to talk about the details of this. I can give a whole other talk about it, but these terms should come from that, these 2 terms. And finally, there's this logarithmic term in n, which is the only thing that is not a power series. It's not a power law, it's a logarithm. And you can wonder how it comes about. And what these people showed is that it actually comes about by studying one loop effects of the light fields of 11D supergravity. So essentially what you do is you fix this background, ADS4 times the sphere, and you study the graviton, the gravitino, and the 3 form of supergravity. You treat them as weakly coupled quantum fields, and you let them run in a loop. And the one loop path integral, if you do it carefully, will give you this 1/4 log n. And that's it. Essentially, we don't know how to compute anything else in the bulk, any of these ... We know all of them from the field theory answer, but at the moment, at least, as far as I know, they have not been computed from the bulk. I should say that there is an attempt to do exactly what I was asked about, to do supersymmetric localization in ADS4 supergravity. And so some people claim to reproduce this whole area function in this way, but okay, I think there's a host of issues with this paper. It's a nice idea, but yeah, I'm not sure I fully believe what they do. Let's put it that way. All right, good. I should say one thing that's important, no one has asked me about this, but if you teach quantum field theory, everything that I computed so far is usually called 1 in quantum field theory. Because this is the path integral of the theory, let me remind you, without insertion of any sources. So if you fix the theory, if you fix k and n, this is a pure number, which usually in quantum field theory, we just normalize to be 1. So you can be a little bit more ambitious and say, can I compute something that knows about excitations in the theory? Something that is not an empty path integral. And so people have actually studied this. And of course, the problem is very hard because I have a strongly coupled quantum field theory. But you can again appeal to these SUSY localization tools. So if you're careful enough to add sources to the path integral that are compatible with the supersymmetry, you can again recycle the same tools and get a matrix model and try to solve that matrix model. So it's not easy. So there's various bells and whistles, what should be done, what should not be done. But what emerges out of a whole series of works is that, again, the answer seems to organize itself again into an area function in the limit of fixed k and large n. But now the arguments of this area function, this c and b parameters, depend continuously on these sources that I'm turning on. Let me quickly say what I'm turning on. I'm turning on a very specific squashing parameterized by this b. So I'm taking the round sphere, which has SO4 invariance, isometry, and I'm squashing it in a very specific way, making it an ellipsoid, keeping U1 times U1 isometry only. And this very specific squashing is compatible with a certain supercharge, which allows me to do the calculation. This B parameterizes the squashing. When B is 1, I have the round sphere. And then in addition, you can turn on certain scalar operators, which look basically like mass terms in the theory that break the conformal invariance. And they're called M1, M2, and M3, and they can be parameterized in this way. So the answer organizes itself into this way. And this is an answer now where I'm turning these 4 types of sources, the 3 masses and the 1 squashing, and I can just compute again the path integral in the presence of the sources. Good. But this is a path integral now of a non-conformal theory. I've broken explicitly the conformal invariance on a manifold.
Question. So how much of supersymmetry is preserved by this?
Yeah, there are 2 real supercharges, 2 real Qs preserved.
Okay, out of 6.
Out of 24. Out of 24. Yeah. It's useful in these games to count real scalar supercharges to not get confused. There's no Lorentz invariance here anymore, so the usual representation theory of the superconformal algebra is out the window. So I'm keeping some specific components of the Qs in general.
Okay.
And then if you tune the masses in a certain way or the squashing, especially in this work of Minahan and students, they really carefully understood for which specific values of these parameters you have enhancement of supersymmetry. But this is not important for my talk. But yes, this can be studied in detail. But you can ask more physically, what is this good for? It's some very unnatural observable for normal quantum field theory people, right? You put the model on a Euclidean sphere. I don't even have a Hamiltonian anymore. I'm squashing the sphere, and I'm computing some path integral. What is this good for? And one thing that is good for is that this thing that I just showed you what the answer is, encodes in some very specific way integrated correlation functions of the conformal theory itself. So I don't have the time to explain all the details. I will illustrate it with the simplest example I know of. So let's turn off these masses, so no masses, but I keep on the squashing switched on. And then I take this answer from the previous slide and I expand at large n. And then you'll see here that the parameter B appears. And so you can take this answer, which I know to all orders in 1 over n, and out of it extract the only dynamical information of the 2-point function of the energy momentum tensor in flat space. So for a 3D CFT in flat space, this is kind of a review, the 2-point function of the energy momentum tensor is completely fixed in terms of the conformal invariance, completely fixes it up to one unfixed number, the coefficient in front, which is usually called CT. And this coefficient is in general very hard to compute in interacting quantum field theory. And in this example, I can very easily compute it to all orders in n by taking 2 derivatives with respect to the squashing and putting the squashing to vanish, turning off the source. It's very easy to understand why. Every derivative brings the operator that couples to the source, and that operator is the energy momentum tensor. And so 2 derivatives will have something to do with the correlation function, the 2-point function of this operator. So in this way, actually, there's a whole industry of trying to understand how this kind of an answer, this kind of a complicated function of the sources, encodes integrated endpoint functions of the ABJM model. And this has been explored by these people and many others, but I don't have the time to talk about this much.
Yeah, but just minor comment. Yeah, so the words integrated is important here, but for this simple correlator, because you are considering free energy, so free energy is you expanding in small metric will be integrated correlators. But
exactly.
For this 2-point function, it's kind of easy extract.
Yeah, this is why I have it on the slide. So if, for instance, if you want to make connection with the 3-point functions, I cannot do this on one slide. So in this work, they have done it all the way up to the 4-point functions. But it gets increasingly hard to extract what piece exactly of the 4-point function you are actually able to extract out of the results. So I'm not saying it's easy or obvious. I'm saying that in some cases it's possible. Yeah.
But you can also get this from supergravity point of view or whatever.
Absolutely. The leading term you can easily obtain by studying the propagator of a graviton in 11D supergravity. But what I want to emphasize, and maybe it's not clear from here, I can give you a closed form expression for this CT valid at all n.
Okay, yeah.
To all orders in 1 over n, which I don't know how to get in any other way. Yeah. Good. Good. So this was essentially half of the talk. I gave you an idea of how to compute the path integral without sources and with sources for this ABJM model. But this was the path integral on the Euclidean sphere on S3. And you can, once you know this, you can naturally ask, can I do this for other manifolds? And if I can do it, what kind of a physical observables I'm encoding in these calculations? Okay, so I'll give you now another example that we were able to compute. It's called the ABJM topologically twisted index. It's kind of a funny name. I'll try to explain what this is. So now I'm changing the manifold. I'm keeping the theory the same, but I'm putting it on this manifold, which is again a Euclidean space, a circle times a Riemann surface. So the Riemann surface, I'll assume it's compact, no boundaries, punctures, anything, and it has a smooth metric on it. And then when you do this, if you don't do anything else, if you just put a SUSY theory on such a space, you're going to break supersymmetry because well, general Riemann surfaces don't admit killing spinors. So you will not have a generator of a supercharge. But Witten, as usual, or as often happens, comes to save the day. What he observed is that if you have enough supersymmetry, n equals to 2 in this case, or higher, you have an R symmetry. So you have at your disposal, you have a background gauge field and a background metric. So the metric on this Riemann surface is non-trivial, but you can imagine also turning on the background gauge field and trying to cancel the spin connection on the Riemann surface. And indeed, if you have enough R symmetry, you can do that. And then essentially you can automatically solve the killing spinor equation because now you've canceled the spin connection with a background magnetic field. So I turn on a flux on this Riemann surface in such a way that I don't have a curvature anymore. At least from the point of view of the spinor, I've canceled the curvature, and so I now have a generator of supersymmetry. And this is called Witten's topological twist. It's a little bit of a funny name because it's not always true that you do get a topological theory afterwards. So if you do this on this example, you still have dynamical degrees of freedom on S1 because I'm doing nothing on this S1. Okay? So anyway, so I'm doing this 3D QFT now on this kind of a space with some specific background fields, and I'm keeping a certain amount of SUSY, which is actually exactly the same. 2 real Qs are being kept. And then these people showed how you can apply the same logic of supersymmetric localization to compute the path integral of this kind of models on this space. So here's the answer. It's again some kind of a matrix integral, but it looks quite a bit more complicated than the previous one. You don't need to understand any of the details. I just want to show you that there's an explicit expression that you can aim to compute, but it's not easy to calculate this. What happens here is that I again have some integrals, but I also have some sum of products. The reason is that now I have a 2 cycle. I have this Riemann surface, and on the Riemann surface I can have gauge fluxes. Remember, I have two U1 times U1 gauge fields, and each of them in the path integral I have to sum over all the possible configurations of the gauge fields. So these are some kind of analogs, if you wish, of instantons in this 2+1 dimensional gauge theory. The parameters delta are very much the same masses that I showed you before, but I now have also new parameters, these n's, which are background fields for the flavor symmetry. Okay? So these NAs are quantized in a certain way, and they have to add up to this curly G is the genus of the Riemann surface. Okay, so I need to find ways to evaluate this integral at large n. This is the name of the game, and this was done again by the first paper here actually also emphasized in a very nice way. There's a rewriting of these integrals using fancy versions of the Cauchy theorem as a sum over residues. So this formula here that I'm showing is not a large n formula. It's valid for all n, and it's a rewriting of these integrals that look very nasty in terms of residues. You have to do some very specific contour integration and so on. The details are not important, but what's important is that there's a conservation of evil. I've told you, I've given you here a simple expression for the answer as a sum. However, what's hard is to find the residues. To find the residues, you'll have to solve these complicated algebraic equations, nonlinear, and for some reason, the authors of the paper called them the beta ansatz equations. We can talk later where these are actual beta ansatz equations for any integrable system or something, but at the moment, think of them as some complicated algebraic equations, which I have to solve for x and x tilde. So y1, y2, y3, and y4 are the background, whatever, masses and sources, and these x's are the things that I have to solve for.
I'm sorry, I think I missed that. Maybe you have said that. So you're really considering index. So on S1 you assume periodic boundary condition.
Very good. Yeah, it's a little bit morally what you're saying is correct, but it's a little bit more subtle. I have not explained this on this S1 because the fermions are charged obviously under the S1 rotation, but they're charged also on in the R symmetry space. So there's some periodicity conditions that combine the periodicity on this S1 with the charge on the U1R symmetry. Yeah, but morally it's
okay, yeah, thank you.
Let's call them supersymmetric boundary conditions on the S1. They involve a phase under the U1R. Yeah, good point. But this is importantly, this is not a thermal path integral. For a thermal one, I have to do antiperiodic, right? Yeah. Good. So I need to find a way. One thing that I can try to do is to solve these beta ansatz equations. Like if you fix n to be 5, let's say, you can just put this system of 5 plus 5 equations in Mathematica and ask it to find you a solution, and it will find you many solutions. And okay, this will be some, all of them will contribute to the path integral, and this will be your answer. But the expectation is that at large n, something special should happen. There should be some kind of a saddle point approximation, and there should be like a unique solution, a special solution, the dominant large n solution. And this is the kind of thing that we would like to understand. And these authors, actually, they didn't use the beta ansatz equations. They went back to the matrix integrals and treated them in a saddle point approximation. And they found analytically these eigenvalue distributions. So now you view this axis as some kind of a continuous eigenvalue distribution, and there's some scaling with n here, and there's a real part and an imaginary part, and they were able to find these t and v explicitly. Okay, so this was done, and if you put this answer for the x's back into the matrix model, you're going to get the leading n to the 3/2 behavior of the path integral. And then you're kind of out of steam to compute the subleading terms. Okay? Remember, for the sphere, what I was able to do, or other people were able to do, was to appreciate some connection with the free Fermi gas, some integrable model, and they used those tools to compute the final answer. Here, at the moment at least, we don't have such tools. So in the absence of intelligent approaches, what we decided to do here in Leuven is to attack this on a computer. And so what we did is, it's a very obvious idea, but it just has to be implemented on a computer in a reasonable way. So what we did is we took these equations at large n. So for us, a large n is probably n equals to a few hundred. So we have to solve a system of, let's say, 1,000 equations. So n is equal to 500. And of course, if you ask a computer for such a system of equations, find me all of the possible solutions, it will not happen in any reasonable time. But what you want is not all of the possible solutions, you want the large n solution. So what we ask the computer is to find the root of the special solution that is the closest to this one, which we know analytically, and which is supposedly the solution at infinite n. Okay? So that was our method, basically. And we did this many times. Many times, really a lot. And out of the numbers that we got, so we obtain a solution, we put it back and we compute the path integral, we do it again and again and again. And out of this, we were able to guess an analytic formula. So this is some kind of an art. I don't know of an algorithm how to do this, but we had an inspired guess. And so this is the full answer. So if you wish, this expression here for f is the analog of the Airy function that I showed you before. It's the full resum to 1 over n expansion to all orders. That's our claim. And it is a function of these parameters, these masses, and these fluxes, and so on. And again, you observe that it is given explicitly resummed as some function of not n, but what we call n hat, some kind of a shifted version of n in this way. Okay? So this expression fits on a line, but it's still somewhat complicated. So for the next couple of slides, I will explain the simplest limit you can take of that expression. So the simplest index is when you turn off all of these extra parameters, the masses and the flavor symmetry fluxes and so on. So if you wish, this is kind of an analog of the round sphere empty path integral. And then the answer is very simple. There's this n hat to the 3/2 term, n hat to the 1/2, and log of n hat. And again, this n hat is not n. So in terms of a large n, it's an infinite power series, which we were able to resum. And this function f hat of 0 is the analog of this curly a function that I had for the Airy, for the round sphere. This one we couldn't really compute in closed forms. We expect some transcendental numbers. Before I had some infinite sums with Bernoulli numbers. Here we are able to expand it at large K and compute the first terms. If K is small, if K is 1, 2, 3, 4, we can compute this f0 hat to arbitrary, to like 30, 40 digits. So we have very good control over this, but we don't have an analytic formula, so to say. And then all of the things I'm saying are extracted out of numerical data, so to say, but we have checked that they're correct because they're accurate up to exponentially suppressed terms. And in some cases, we can actually compute these exponentially suppressed terms also.
May I ask a quick question? So for k equal 1,
Yes.
the this superconformal index was discussed in the literature. So for generic chemical potentials, etc. How this is related? Is there a relation, or you're basically generalizing this to any case?
I'm not sure if so this is not the superconformal index. First of all, this is a simpler index, essentially because the superconformal index, if you wish, counts BPS operators in the three-dimensional ABJM theory.
Yeah.
This object, because of this twist here, physically what I'm doing is I'm first deforming ABJM to some effectively 1D quantum theory, and then counting the states in this effective 1D theory.
Okay.
Okay, and as far as I know, no one was able to compute anything with this for any value of k beyond the leading n to the 3. So this thing that I showed you here analytically will give you the n to the 3 half term, and only that.
Okay, so there you have a parameter like beta, or temperature, effective beta parameter, which is the radius of S1. So here you don't actually have continuous parameter like that.
I don't. In fact, also for any of these indices, they're independent of the radius of S1 because of supersymmetry.
Okay. Yeah. Okay.
So that's why if it was a thermal path integral, of course, that would be a complicated function of the temperature. But here, I just don't see any dependence on the size of the circle. And this will be very nice when I speak about the ADS bulk, where this will be manifest, that there wouldn't be a dependence.
Okay, thank you.
Yeah, good points. Obtained so the claim is that essentially what we obtained is some kind of an analog of this Airy function, but for a new observable, this index on this space. And again, just like before, I can try to think of this as a string theory path integral now. Do this semi-legal operation of taking now k and n to be both large and their ratio to be fixed. And then in a very nice way, I again could resum these answers in functions that should be thought of as the free energy of the type 2a string on a different background, not on MTADS, on some other background, which is a black hole, actually. And then we could compute these to any order that you like. And again, they resum nicely in terms of the same shifted lambda minus 1 over 24. And of course, if you're a string theorist, one day you should try to answer how do you compute these things, not from the gauge theory side, but actually from the type 2a string. I don't have any good ideas at the moment how to do that. All right. This was like the QFT part of the talk. So I'll try to explain now what do these results imply for ADS CFT. But if you have questions at this point, please ask me. No? Okay. Good. Now, here is a simple solution of four-dimensional supergravity. So this is a Euclidean 4D solution. It is a solution of what I want to call 4D minimal supergravity. So only the this is essentially Einstein-Maxwell theory. I have a metric, I have a U1 Maxwell field, and I have a gravity. Two actually, but anyway. I turn off the fermion, I have the metric, which is given here, and I have the Maxwell field, which is given here as a two form. And I claim that what I've written on these two lines is a supersymmetric background of this 4D supergravity theory that has two real supercharges. What is kappa? Kappa is the normalized Ricci scalar of the Riemann surface. So when kappa is 1, this is the sphere. When kappa is 0, it's the torus. And when it's -1, it's some hyperbolic Riemann surface with the Einstein metric on it. Okay? And the parameter Q is a real number, which you should probably think as the electric charge. The magnetic charge is fixed. It's not free for you to choose. And this is the manifestation of supersymmetry. Essentially, the magnetic charge is related to the mass in a very specific way. And I'm sorry, this G is 1 over L. I was calling big L was the length scale of ADS, and this G is 1 over that. Good. So this is an explicit solution. You can check that this solves equations of motion, the BPS equations, it's all good. You can ask, when is the solution smooth? What essentially happens is that there's a circle tau and a radial direction r, and as you go into the solution, it looks like a cigar. So the circle shrinks smoothly to 0 size as long as q is bigger than this kappa, and then the periodicity of tau is completely fixed in this way. So the way to think of it in terms of a picture is that I have a cigar, and then the Riemann surface goes along for the ride and has a finite size. At infinity, I have asymptotically empty de Sitter 4, and then it smoothly caps off in the middle somewhere. Then you can compute with the usual tools the on-shell action of this solution, and spectacularly, for me at least, the on-shell action is independent of Q. It's independent of the radius of the circle, which is intimately connected to what Arkady asked me about. What you learn is that for this is a family of supersymmetric backgrounds parameterized by Q. For all of them, the on-shell action is the same and is given by this very simple formula. And then you appreciate that when you take Q to 0, this Euclidean background develops an infinitely long throat, and this looks like instead of a cigar, it looks like an extremal Reisner-Nordstrom black hole. And indeed, it's exactly that. So for Q equal to 0, this is the extremal magnetic Reisner-Nordstrom black hole. And what we've done here is we've computed its entropy by computing this on-shell action. It's minus this on-shell action, as we learned from the famous work of Gibbons and Hawking. Okay, so this is a collection of facts about this simple solution. What is interesting now is that I can take this 4D solution and think of it as a solution of 11-dimensional supergravity. There's a specific way to uplift it to 11 dimensions, and this is how you should do it. You take the metric on the previous slide, you attach a CP3, and then you attach a U1 bundle on top of the CP3, and in addition, this Maxwell field which I have for 4D becomes a Kaluza-Klein vibration, if you wish. So this is an additional vibration of the circle over the Riemann surface that is inside of this 4D space, and then there's a corresponding expression for the 4-form flux. And this J is the Kähler form on CP3. So this is an explicit analytic solution of 11-dimensional supergravity. And the results I showed you for this index should be interpreted in ADS CFT as some kind of an answer for the path integral of M theory on this background. Okay, so this sounds like a big claim I'm trying to make. Let's see if it's actually true. So you can do is you can take this index that I showed you before, expand it at large n, and try to understand how to compute these coefficients from the bulk, from this 11-dimensional solution. And this can again be done, otherwise I wouldn't be giving a talk here. And the leading term is simply the on-shell action of the black hole, what I showed you on the previous slide. So in some sense, this index explains the entropy or computes the entropy of the black hole order by order in 1 over n. The subleading term is again associated with some higher derivative terms, and this logarithm of n again can be understood as a one-loop contribution from the weakly coupled supergravity modes on this background. And again, the ... I don't have any tool at the moment, at least, to compute them from M theory or 11-dimensional supergravity. But we know this index, so it's natural to conjecture that we know the all-order expansion, and we're just waiting for someone to understand M theory to compute it for us. Okay. I don't have much time to tell you about this. There's some people here interested in black holes, so maybe just a few comments. You can ask wait a minute, in the QFT side, you had all of these delta 1, delta 2, delta 3, delta 4, these fugacities, these masses. Where are they in 11D supergravity? They can be included, but then the calculations get much more nasty. For every source that you want to turn on in the quantum field theory, ADS CFT instructs you that you should excite a bulk field, a corresponding classical field in 4D supergravity, and then you should solve Einstein's equations, and you should keep the thing supersymmetric. So it gets a little bit ugly, but we were able to do this, and we're able to find what we call black saddles. So these cigar-type Euclidean solutions with some scalar fields. This is the standard STU model of 4D supergravity, for those of you who know what this is. There's some 4 Maxwell fields, 3 complex scalars, and you have to solve for all of the functions that I'm giving you here. And we managed to do this with 2 people here in Leuven, and the leading order answer on the nose at large M, on the nose agrees with the index. And at the moment, at least, we don't know how to compute the subleading terms using higher derivative supergravity, because it's very hard to construct these extra multiplets to incorporate them into this formalism of, corrections to supergravity. And again, just like before, these Euclidean solutions, if you treat them in a specific way, they have as a limit the usual black holes in ADS4, which have near horizon ADS2 regions and so on. So you can make a connection with black holes again.
So previously you had a vanishing result for G equal 1.
Yeah, very good.
So could you comment on that and how you see that here?
Yeah, indeed, this is a very good question. I was not lying to you for the past 1 hour, but I was sweeping things under the rug. So G equals 1, I have to go back to the matrix model. G equals 1 is a special case. So already this formula here that I showed you has to be treated carefully when G is equal to 1. It's strictly speaking not valid for G equals 1. Because essentially on the torus you have extra zero modes, which you should treat as new quantum fields, and you should incorporate them. So everything I've showed you is true for G not equals to 1. G equals 1, people can do it, but I have to give you separate expressions on each of the slides, and I don't know. I don't want to do it at the moment. Yeah, but good point.
But with these deltas, you don't have G equal 1 as explicit. It's somehow hidden in this relations, I guess.
It is deltas add up to 2. They are independent of the genus. These fluxes depend on the genus.
Yeah. Okay.
And essentially, what happens is that these background magnetic fluxes, when they add up to 0, you have extra zero modes of some of the fields of ABJM, and it gets a little bit, it gets more annoying as usual with extra zero modes. So if you wish, just for on the moment, ignore the torus and study anything else for a Riemann surface. That I think is the way to understand all of the formulas. Okay, good. What I want to very quickly tell you is that none of the things I told you about are specific to this ABJM model. There's other models that people have studied of 3D supersymmetric CFTs, which are arising out of M2 branes, so are relevant for ADS CFT. And we studied a bunch of them, and for all of them, we have these kind of nice expressions for the index. This one is probably the simplest one of them. It's a slightly different model. You don't have a Chern-Simons term. You have the usual Yang-Mills term with one adjoint hypermultiplet and NF fundamental hypermultiplets. This is a 3D n equals 4 usual gauge theory. And the claim is that at low energies, this will flow to a CFT. And that CFT will have something to do with M2 branes on this kind of a space. So now, again, I have some kind of an orbifold of C4. However, now the orbifold acts in a different way, and this actually has a fixed point on the sphere. So this manifold here is not really a manifold, it's some kind of an orbifold. Anyway, for this model, we can again run our algorithms and compute this index and resum it into a one-line expression. And again, there's a corresponding black hole, which is asymptotic to this kind of a space in 11 dimensions, and things work out. And then once you know this, and if you have good students or collaborators, you turn the crank, and you can do, we could do it for all of these examples. I'm not going to explain what these examples are. The point is that this is not specific to ABJM theory. It just works on all examples that we looked at. Good. Now to something that Arkady asked me, the superconformal index. This is a much more complicated object, and there's a good reason for it. It's an effect. It's a 3D path integral, and you have a U1 action, which you can think is in some. You can think of it as a translation on this S1 as a Hamiltonian. So you're actually counting states. You're computing some kind of a partition function, and the states you count are 1/16 BPS operators in ABJM. So we don't have a closed form answer in general. No, the way to think about this index geometrically is as a path integral on a product. It's not really a product, it's more like a vibration of this S1 over this S2, but it's on this Euclidean space, and the parameter omega, you can think of it as angular velocity on the S2. So these BPS operators, they can have a quantum number over this S2, a spin, and this is what this omega actually counts, or is the chemical potential for that spin is omega. Interestingly, this omega is related because of supersymmetry to the radius of the circle, to the length of the circle. And so you can try to think of a Cardy-like limit. So the usual Cardy limit in a thermal 2D CFT is to take the radius of a thermal circle to go to 0. So here you can try to take the radius of this S1 to go to 0. And this amounts to taking this omega going to 0. It's not immediately clear that this is a good idea to do, so one has to experiment a little bit. But if you do it, you find that actually, term by term in this small omega limit, the matrix model that controls this index, which I'm not even presenting here, simplifies, at least for the first two terms. It actually, we're able to massage it in a certain way, such that we can compute it to all orders in 1 over n, again, and resum it. So this is a weaker result from what I showed you, because I don't know how to compute these subleading corrections in the small omega limit. And there is an infinite number of them. We're able to show that the series in omega doesn't stop. So you have infinitely many terms, and at the moment, I don't know how to compute them. But at least the first two, I can, and I showed the result here. The claim to fame of this index is that it captures the entropy of another black hole, the Kerr-Newman black hole, the extremal Kerr-Newman black hole in ADS. So in the limit of a small angular velocity, this result at large n agrees with the entropy of the Kerr-Newman black hole. And again, I can do this for all these other n equals to 2 theories I showed you about. Okay, final slide. I think I'm almost on time, so if you give me 2 more minutes, I will tell you about thermal observables. Is that okay?
Yeah, sure.
Okay, good. So far, everything I told you about is supersymmetry was heavily used in essentially every calculation, but you can try to be more ambitious, or at least try to ask questions like the following one. Suppose I have a CFT, usual 3D CFT, don't assume any amount of supersymmetry, and I want to put it on the following thermal background, S1 times a plane. The periodicity of this S1 in the usual way should be related to the temperature, and then conformal invariance is explicitly broken. I've introduced a scale, T. But there is a notion of conformal covariance. So now the one-point functions of primary operators do not vanish anymore. At the conformal point, they have to vanish. But as I turn on t, they do not have to vanish, but their dependence on t is completely fixed by their conformal dimension. So this 3 here is not an accident. This is the 0, 0 component of the energy momentum tensor, and its one-point function scales with t with the power 3. This is fixed by the conformal invariance. Okay, so but the coefficient bt is not fixed by anything. This is dynamical information about your quantum theory that you have to somehow compute, and that's hard for interacting quantum theories. This coefficient is actually essentially the same up to a factor of 3 as the free energy on this of the theory on this kind of space. So because I have infinite R2, this should be called really free energy density. So this Ft is the free energy density of this model of the CFT. So you could ask, how do I compute these quantities for the ABJM theory? Can I do it? From the QFT side, as far as I know, there's no tools to do this because it's a strongly coupled QFT. It's not something like an ON vector model where you can relatively easily apply 1 over n perturbation theory. So I really don't know how to compute these things. But I have ADS CFT, so I can appeal to the bulk and try to compute it. It's relatively easy to do this for the leading n to the 3 half term. So these BT and FT are going to scale in the same way with n as the SUSY observables. But then if you want to push this to subleading orders in n, it's hard. And what we did is some kind of a trick where we use what I told you about in the past 1 hour, use this supersymmetric localization result to effectively fix the higher derivative supergravity couplings. And once I have a supergravity Lagrangian with the corrections explicitly known, I can then apply that to a non-supersymmetric solution. So the Lagrangian is actually supersymmetric, but the solutions of the Sugra theory may not be supersymmetric, may be thermal. And so applying this very simple idea, in this case, we were able to compute this number, BT, the subleading term of this number. The leading term was actually computed by Arkady 27 years ago, I think. But the subleading term is, we were able to do that. And well, we find a somewhat surprising thing, maybe, I don't know. To me, it was a surprising thing that this BT, which is this one-point function, is really proportional to the 2-point function of the energy momentum tensor in the conformal vacuum. So there's no reason for this to be true. It's certainly not true for the ON model or the Ising model or something. And it seems to be true at least to this order at large n in this ABJM theory. I don't know the reason for this. I don't know when it's going to break down, but the expectation is that it's at some point at finite n, this will no longer be true. But anyway, it's an open question. And again, I can do the same thing for all these other CFTs arising from M2 branes. All right, that's the end of the story. Here is a quick summary of what I told you about. I told you how to compute 3 types of path integrals of the ABJM theory on compact Euclidean manifolds using SUSY localization. I told you how this relates to ADS CFT in some way. In some cases, when the thing looks like an index, looks like a counting function, the results are related to the entropy of supersymmetric anti-de Sitter black holes. And okay, you can extend this to other models. And finally, in some cases, for some specific observables, you can access non-supersymmetric information about the theory. There's a lot of things you can ask and you can attempt to do, extend this to other holographic models that are not in M theory, that are in massive 2A string theory or in type 2B. We're trying to think about this at the moment. Again, some of the things I told you about are purely numerics. It would be nice to understand them analytically. At the moment, I don't know how to do it, but hopefully there's a way. You can try to think about other compact Euclidean manifolds, there's a whole interesting story I've been emphasizing in the talk, that n shifts in a specific way, that lambda or alpha prime shifts in a specific way. It would be nice to understand this from string or n theory, why this happens and how it happens. We have some ideas how to do this, and there's some work already published on this, but the full story is not clear to me. You can try to, someone asked me about SUSY localization in 4D. I think it's interesting to study this. I don't have much to say. Well, and there's more esoteric type of questions, what we actually learn about type 2 string theory or n theory. I showed you some answers, which one day should be computable in string theory, but I don't know how to do it. So it's just, raising questions at the moment. And finally, there should be something like OSV type conjecture for the entropy of anti-de Sitter black holes. So OSV is a relation between the partition function of a topological string and the entropy of an asymptotically flat supersymmetric black hole. I feel like there should be a version of it for ADS black holes, and it will be nice to understand. That's all I had to say. Thank you very much, and sorry for going over time.
Thank you. Are there any questions?
I have a comment about the last part. So let me see. So let's start with the usual D3 brane, N = 4 sub-Young-Mills. So the free energy, similarly, you get formula which there is some function of lambda times power of temperature times the volume. And in a paper with Gapser and Klebanov, we computed the leading term and subleading term, which is coming from R and R4 corrections in 10 dimensions. And there, indeed, there is an issue whether we get the coefficient precisely, because we need to know precise flux-dependent terms in 10 dimensions. But basically, the computation is just computing the action on black hole in ADS. So similarly, I think in our paper we had comments also on 6 dimension, 3 dimensions similarly. And you get basically this n3/2 plus n1/2. But that was, at that time, it was definitely only referring to M2 brane will K = 1, basically, language. So, that's pretty nice that you manage actually to get the coefficients precise for the subleading term. But this connection to, so the logic would be if you do this in 11 dimensions, if you know supergravity term plus R4 term with all flux terms, relating it with all coefficients known, then you will reproduce this formula.
But we don't know them, right? So that's
but you did it via low compactifying on the complex space. So, I understand. I understand the logic is it's a very nice way of fixing this freedom from what is known. But let me ask a question now. So suppose you know this action precisely. So then you can take this action and evaluate it on a black hole. You'll get your expression for BT. But you can also take that action and evaluate, say, 2-point function of small metric perturbation. That will give you CT. Since they come from the same action with the fixed coefficients, at least for this R plus R4 term, I would expect maybe that's the reason why they are connected.
Very good. So what you're saying sounds a lot like my intuition. However, what makes it not obvious, to me at least, is that usually to compute, how to say, now that I've added higher derivative terms, computing graviton propagators becomes a little bit of a tricky business, right? And so in some sense, I have assumed that I have this big mess of the R⁴ and all the fluxes, assumes I know all of the coefficients, as you say. The solution that you use to compute this BT is this ADS soliton. It's not even a black hole. It's a very simple, it's almost like empty ADS. So I'm using a very simple solution, and I would expect that many of these complicated terms are actually going to contribute 0 to the on-shell action. However, it's less obvious to me that they're not going to contribute. Some of the things that contribute 0 to the on-shell action may actually contribute to the two-point function.
I agree. Yeah. So a priori,
what we find is that should not happen, at least at this order, for some reason. I don't understand why, but yeah, I mean, there is a very nice paper actually by Petku from 30 years ago, who took the OM model at large N and computed essentially what I call CT and PT, two leading order in 1 over N. And then already in that you know, using usual Feynman diagram rules and so on, and already there he saw that these two things are not equal. So it is certainly not a property of general CFTs, even at large N. So I don't have any more intuition than
but can you think of doing the same for N equal 4 theory? Because to my mind, there was no independent computation for the subleading term.
Yeah, very.
I mean, this zeta 3 term.
Very good question. The problem, so this trick that I did not explain at all, this thing in green, but you've heard a talk by me at some other time when I was explaining it. This trick, we have done it exactly the same in ADS5. However, the structure of the answer is very boring. I mean, to me, everything is fixed in terms of anomalies. So the on-shell action for any asymptotically ADS5 background comes out completely fixed by the A and C anomaly coefficient. You now have access to both A and C, not only to A equal to C, but you don't have access to anything else. So in particular, with this 5D lower dimensional supergravity approach, I cannot access any dependence on lambda because A and C are independent of lambda. So it's kind of very annoying to me. I was hoping that I'll have a tool to access the alpha prime expansion from 5 dimensions, but what comes out is less interesting than that. So unfortunately, the answer to what you're asking is no, but I wish I could find a way to do it. Yeah, it's a very good good thing to understand, but I don't know how at the moment.
Okay, thank you.
Yeah.
Any other questions?
But do you have any reason? Let me ask you a question, since it's a little bit informal. Do you have reasons to doubt what you computed 27 years ago?
No, but we made some assumptions about, for example, we assumed everything there exists a special scheme in which everything is controlled by wild tensor, etc.
I see.
Yeah, so in principle, it would be interesting. And then the same question is about 2,0 theory, where it's NQ plus N. Yeah, so that would be the same. There, I think there, our coefficient may not be, well, we also gave some expression for the order N coefficient, but
unfortunately, in 7D supergravity, the tricks we used in this thing that I call unreasonable effectiveness slowly start to fail because I cannot use conformal supergravity. There's very few papers, and it gets uglier for ADS 7. But indeed, it will be interesting to try to get another handle on these questions. Yeah.
Okay, I don't see any other questions. So then, thank you for a nice talk.
Thank you so much for hosting me.
Thank you.
Thanks.
Goodbye. Bye.
Thanks.
Bye.
До свидания.